Welcome to the Natural Language Processing series. In this first chapter, we'll explore the fundamental concepts that form the foundation of modern NLP. Natural language processing, or NLP, is the field of artificial intelligence that focuses on enabling computers to understand, interpret, and generate human language. From chatbots to translation services, NLP powers many of the technologies we use every day. By the end of this chapter, you'll understand how raw text is transformed into numerical representations that machines can process. So what exactly is natural language processing? At its core, NLP is about bridging the gap between human communication and computer understanding. The typical NLP pipeline starts with text input, moves through preprocessing and analysis stages, and produces meaningful output. Common applications include machine translation, sentiment analysis, chatbots, and document summarization. NLP has evolved dramatically from rule-based systems in the 1950s, through statistical methods in the 1990s, to today's powerful deep learning approaches. Each era brought new capabilities and improved accuracy. Tokenization is the first and most fundamental step in any NLP pipeline. It's the process of breaking text into smaller units called tokens. There are several approaches to tokenization. Word tokenization simply splits text by spaces and punctuation. Subword tokenization, like byte pair encoding or BPE, breaks words into meaningful subunits, which helps handle rare words and morphological variations. Character tokenization treats each character as a token. Modern transformers often use special tokens like CLS for classification, SCP for separation, PAD for padding, and UNK for unknown words. Word embeddings revolutionized NLP by representing words as dense vectors in a continuous space. Unlike one-hot encoding, which creates sparse vectors with thousands of dimensions, word embeddings capture semantic meaning in just a few hundred dimensions. The famous king minus man plus woman equals queen example demonstrates how these vectors capture analogical relationships. Words with similar meanings cluster together in this vector space, and we can measure similarity using cosine similarity. This mathematical representation of meaning enables machines to understand language relationships. Word2Vec, introduced by Google in 2013, was a breakthrough in learning word embeddings. It uses two architectures, CBOW, or continuous bag of words, which predicts the center word from surrounding context words, and skipgram, which does the opposite, predicting context words from the center word. Both methods use a sliding window to capture local context. Training Word2Vec is efficient and scalable to large corpora. The learned embeddings capture not just similarity, but also semantic relationships. Using libraries like Gensim, you can train custom embeddings or use pre-trained models. GloV, which stands for Global Vectors, takes a different approach to learning word embeddings. While Word2Vec learns from local context windows, GloV leverages global co-occurrence statistics across the entire corpus. It constructs a co-occurrence matrix counting how often words appear together, then factorizes this matrix to learn embeddings. This global perspective helps GloV capture broader patterns in language. Pre-trained GloV models are available in various sizes, from 6 billion to 840 billion tokens, trained on sources like Wikipedia and Common Crawl. TF-IDF, or Term Frequency Inverse Document Frequency, is a classic method for measuring word importance in documents. Term frequency counts how often a word appears in a document. Inverse document frequency measures how rare a word is across the entire corpus. The product of these two values gives us TF-IDF. Common words like the get low scores despite high frequency because they appear everywhere. Rare but meaningful terms get high scores. TF-IDF is still widely used for document retrieval, keyword extraction, and as a baseline for text classification tasks. Japanese NLP presents unique challenges not found in English. The most significant is the lack of spaces between words, making tokenization much more complex. Japanese also uses three writing systems: hiragana for native words, katakana for foreign words, and kanji for Chinese-derived characters. Morphological analyzers like MICAB, Janome, and Sudachi-Pi are essential tools for Japanese text processing. They not only segment words, but also provide part-of-speech tags and readings. Understanding these challenges is crucial for building multilingual NLP systems. A robust text preprocessing pipeline is essential for good NLP results. The typical pipeline includes lower casing for consistency, removing punctuation and special characters, tokenization to break text into units, removing stop words like the and is, and applying stemming or lemmatization. Stemming simply chops off word endings, while lemmatization uses vocabulary knowledge to find the root form. Libraries like NLTK and SPA provide ready-to-use tools for these tasks. The exact preprocessing steps depend on your specific application. Let's review what we've covered in Chapter 1. We started with the fundamentals of what NLP is and how it has evolved. We explored tokenization, the critical first step in text processing. We learned about word embeddings including word2vec and GLO-V, which represent words as meaningful vectors. We covered TF-IDF for measuring term importance and discussed the unique challenges of Japanese NLP. Key tools include NLTK, SPA-SCI, GenSim for embeddings, and MICAB for Japanese. In the next chapter, we'll dive into deep learning approaches for NLP, including recurrent neural networks and attention mechanisms.